In this video, we are continuing this section on optimization problems that involve a constraint, and we'll do an example where we maximize production. So the example says that a cosmetic company manufactures B shampoo bottles according to a Cobb-Douglas production formula. B equals 40 times I to the 0.3 times H to the 0.7. So Cobb-Douglas just refers to a special type of formula that has this form. One of the indicators of a Cobb-Douglas formula is that these exponents that show up will add up to 1. But we don't really need to know anything about Cobb-Douglas besides that. Just this is the formula that we're going to work with in this problem. Okay, where I is their annual investment in tens of thousands of dollars, and H is the total number of work hours. The annual budget is $2 million, and employees earn $25 per hour. Part A asks to find the number of work hours and annual investment that maximize production. So this question wants us to maximize something. It says to maximize production, and that's what will tell us our objective. The objective is an equation for the thing that we want to maximize or that we want to minimize. In this case, it's the production, and that equation is given to us in the problem. It's B equals 40 I to the 0.3 times H to the 0.7. That was given to us in this question. So now the constraint there is also a constraint in this problem, and I want you to pause the video to see if you can identify, well, what part of the problem tells us the constraint, and then how do I write that with a mathematical statement. So pause the video for about 2 minutes and see if you can identify, well, where is the constraint in the problem, and how do I write that with a mathematical equation. 4, 3, 2, 1, pause that video. Pause it for 2 minutes to really try to set up this constraint. This is often one of the more challenging parts of these optimization questions, converting the word problem to a mathematical statement. So it's important to get that practice even now while watching these videos. All right, so hopefully you've done that. Hopefully you've paused the video for about 2 minutes to really try to answer that. So the constraint portion of this is it tells us the annual budget. And it says it's $2 million. So the budget is $2 million. That's where the constraint is going to get factored in. And there's two things that are contributing to the budget and where the company puts in their money. So they're putting in their money into this investment, this annual investment that they make. And then they pay their employees money for how many hours they work. So I'm going to call that salaries. So, whoops, I misspelled that. Investment plus salaries. Those are going to add up to $2 million. That's their budget on this. So $2 million, $2 million. So it's saying that the annual investment is I, but I is measured in tens of thousands. Okay, so as a quantity, I have to take I and multiply that by 10,000. For example, if I is 3, that means that investment, because it's in tens of thousands, is actually 30,000. It's actually $30,000, for example. So similarly, whatever I is, I need to multiply it by 10,000 if I want to get it in terms of dollars. Okay, and then for their salaries now, H represents the total number of hours all of their employees work combined, because it says it's the total number of work hours. So I'm going to have to factor in the H. But for each hour, they're paying their employees $25 per hour. So I got to multiply H by 25. And that's how much money they're paying towards salaries. So that's going to add up to this $2 million. And that is our constraint. So we have our objective and our constraint equations. So we can handle this either by doing substitution or by doing Lagrange. But seeing the fact that these powers are decimals, I noticed that if I were to substitute into this, I would end up taking derivatives with a complicated thing being substituted in. And then on top of that, I'd have these decimal powers. So I'm thinking maybe the algebra is going to be a little bit extra tedious if I were to substitute. So maybe I'm leaning towards Lagrange, but both would technically work. So if I did Lagrange, remember the objective, we call that f. And with the constraint, I move all the terms to one side. So we get 10,000 I plus 25h minus that 2 million equals 0. And once it equals 0, we call this whole function g. And now we are ready to construct the Lagrangian function. Okay, so we call this function L. But in this problem, my variables are I and h rather than x and y and z. Okay, so the Lagrangian function takes f first, which is 40 I to the 0.3 h to the 0.7. And then we do minus lambda times g. Okay, so let's fit g in here. It's 10,000 I plus 25 h minus 2 million. 2 million, a lot of zeros in this question. All right, so if I were to simplify this, I would now need to distribute that minus lambda to get minus 10,000 lambda I minus 25 lambda h, and then minus 2 million lambda. All right, so the next step I've already written down for us, it's to find the critical points. So we got to take some partial derivatives. So we would take the partial with respect to each of these variables. So with respect to the I, set that equal to 0. And with respect to h, and set that equal to 0. So if I do it with respect to I first, I would do power rule for this I to the 0.3. That 0.3 would come down in front, and I would get that times 40 I to the, when I subtract 1 from 0.3, I'll get a negative 0.7 for the exponent. The h part stays there, h to the 0.7, because h gets treated as a constant when we're doing the partial derivative with respect to the variable I. All right, for the next term, minus 10,000 lambda I. That partial is minus 10,000 lambda, and then the remaining terms don't have I in them, so their partials are 0. Okay, so this is going to be equal to 0. Now partial with respect to h. So power rule says the 0.7 is going to come down, and that will multiply the 40 I to the 0.3, and then we'll get h to the, I subtract 1 from 0.7, and that'll give me negative 0.3. Alrighty, and then out of the remaining 3 terms, the only one that's not going to be 0 is the minus 25 lambda h, and that partial will give me minus 25 lambda equals 0. Alright, so I have my first equation. My second equation, there's 3 unknowns here, I, h, and lambda, so I will need a third equation. And when we do Lagrange, that always comes from our constraint, which remember was 10,000 I plus 25h equals 2 million. Our constraint right there. Okay, so we have the system of equations. Okay, so we know that we need some more practice solving these, so let's pause that video. Pause it for about 4 minutes. It's always good to get practice solving these system of equations and Lagrange problems. This is often the trickiest part, so it's good to get that practice. 4, 3, 2, 1. Pause that video. Pause it for 4 minutes to try to solve this system of equations on your own first. Alright, so hopefully you've done that. Hopefully pause the video for about 4 minutes to really try to solve the system. Let's talk about it together now. So from the first equation and the second equation, what I'm going to do is just rearrange them to get the lambda terms on one side. And I'll also simplify, so like 0.3 times 40, that gives me 12. So we'll get 12, and then we have h to the 0.7. And then if I move the I to the negative 0.7 to the denominator, we get over I to the 0.7. And this will be equal to 10,000 lambda on the right. If I do the same with the second equation, 0.7 times 40 is 28. And we'll get that times I to the 0.3. This time the h goes to the denominator, so we'll get over h to the 0.3. And equals 25 lambda, moving that 25 lambda to the right. Okay, so I can definitely do this, how we've done some of these in the other problems, like isolate the lambda and then set them equal. But I noticed that I can avoid some of the fractions if I were to just multiply the 25 lambda by a number that would make it match up with 10,000 lambda. So I would need to multiply by 400 to make that happen. So I'm going to multiply both sides of equation number 2 by 400. And that will give us 11,200 times I to the 0.3 over h to the 0.3 equals 10,000 lambda. For my second equation, it becomes that. And now we have this first expression for what 10,000 lambda equals. We have this second expression for what 10,000 lambda equals, so we can set those equal. So we'll get 12 times h to the 0.7 over I to the 0.7 equals 11,200 over I to the 0.3 over h to the 0.3. And if I rearrange this a little bit, let's move all the variables over to the left. So I'll get h to the 0.7 over I to the 0.7. And that's going to get multiplied by the reciprocal of this term on the right that's in the parentheses. So that'll give me h to the 0.3 over I to the 0.3. And then that's going to equal on the other side, 11,200 divided by 12. But that simplifies nice, a little bit. I could simplify that to 2,800 over 3 if I divide the top and the bottom by 4. Okay, but the left simplifies really nicely. Because when you have something like, a number to a power times that same base to a different power, to any power really, the exponent rule says you add the exponents. So this is a to the b plus c. So if we apply that exponent rule here, we would get h to the 0.7 added to 0.3, which is 1. Same thing on the bottom, we'll get I to the 1, and that's really nice. So this equals 2,800 over 3. And rearranging this, if I move the I to the right, we'll get h equals 2,800 over 3 times I. So we have this equation, and if I zoom out and look at our system of equations that we had, where could I use this? Well, I noticed that I could substitute it into my constraint. So I'm going to do that. So we will substitute into the constraint. So that was 10,000 I plus 25 times h. And I know what h is. This is what I'm plugging in. H is 2,800 over 3 I. And this is supposed to equal 2 million. Whoops. So my page got shifted there. Okay, this is supposed to be equal to 2 million. Alrighty, so this gives us, if I get a common denominator with a 10,000 and I multiply the top and the bottom by 3, this gives me 30,000 over 3 I. And if I multiply 25 times that next 2,800, that numerator, we'll get 70,000 on the top, 3 on the bottom, and then times I, equals 2 million. And now to the left-hand side, we got a common denominator, so we can add these fractions and get 100,000 over 3 times I equals 2 million. Now we can isolate I by multiplying by the reciprocal of this fraction. So I is 2 million times 3 over 100,000. And this is going to simplify nicely. 100,000 divides the 2 million evenly. And I'm left with 1 on the bottom and a 20 on the top. And that gives us I equals 60. 20 times 3. Okay, and recall, ultimately when I need to write this down, I'm going to need to remember my units. The units of I were tens of thousands of dollars. So let's remember that. Okay, so we can now take this and plug it into our equation for H. So H is going to be 2,800 over 3 times I, so times 60. And 60 is divided by 3 evenly. That'll give me a 1 on the bottom and a 20 here. And 20 times 2,800 gives 56,000. And the units of H are hours. They're the total number of employee work hours during this year. So now we just need to write down our answer as, we just got to write down our conclusion, which is the company's annual investment. We wanted to know the annual investment and the total work hours that would maximize production. So the annual investment must be, let's see, it was 60, the value that we got. Was it? If I scroll it down, I think it was 60 for I. It was 60, but remember that is in tens of thousands of dollars, so I need to multiply 60 by 10,000, and that's going to give us 600,000. 60 times 10,000 is 600,000. And the total work hours must be, and for that it was that exact value, 56,000, to maximize production, to maximize the number of these shampoo bottles that they manufacture in a year. Okay, and part B of this question is going to ask, well, find the maximum number of bottles produced. So to answer this, I need to remember what that original formula was for my objective. So B is the number of bottles produced. And this, whoops, I think I miscopied one of these variables. I think the number of work hours we were calling H rather than W. So this is H. And now I plug in my values. So we'll get B equals 40 times the value of I was 60. So 60 to the 0.3. Remember, I is measured in tens of thousands, and that's why I write 60 here, because that represents 60 times 10,000, which is 600,000. And then H, our value of H, the number of hours was 56,000. So we get that to the 0.7. So if I plug this into a calculator and I evaluate it, it is about 287,896.90 if I round it to 2 decimal places, bottles. So in terms of our goals for this section, over the last several videos, we've talked about how to solve these max-min problems that involve a constraint using 2 techniques, using substitution and using Lagrange multipliers. We have satisfied both of our goals now.